Okay, let's begin by taking a look at dilations. So dilations are also a type of transformation, but they're different than the rigid motions because these involve a change in size. So a dilation is a transformation that shrinks or expands a figure. And we use the letter n as the scale factor, or how much it grew or shrunk. So for example, if it doubled in size, the scale factor would be 2. If it was a third of the length, it would be 1/3. So a dilation preserves angle measures, the shape. So it's still as that same triangle with the same angles, but the lengths are different. So dilations are different. They're not a rigid motion. Okay, so we can see on this picture a lot's going on and a lot of the good notations happening. D stands for dilate, or dilation. N is the scale factor. And C is the center. And of course we have our pre-image and our image. So C is where the scaling is happening from. It can happen from a point on the object, or it could happen from a point distant away. But you can see that these guidelines are showing us where P is going. And the real scaling is happening how CP is becoming CP prime, and you multiply times n to make that change. So as I said, the scale factor of the dilation is the ratio of the lengths of the before and the after. So for example, on our picture when we had PR at first looked like this, but then it was scaled up and looked like this. So the way you get the scale factor is by taking the final divided by the initial, or the length of the image divided by the length of the pre-image. It gives the before and after effect. It makes more sense. So if the scale factor ends up being bigger than 1, then it's an enlargement. So if the image is bigger, it's an enlargement. And if the image is smaller, if the scale factor is a proper fraction, the dilation is a reduction or a shrink. Okay. Is this dilation a enlargement or a reduction? What's the scale factor? So it's important to know what is the pre-image and what is the image, right? So we look at the letters to help us denote that. So this pre-image, as it moved to the blue image, it shrunk. So this is a reduction. And we see that EH goes to E prime H prime, which was a length of 8, which now went to 2. So that means the scale factor must have been a 4th because it cut the 8 in 4 pieces. The notation would be dilate the pre-image by a factor of 1/4, centered at C, which is in the middle. See how it's shrinking towards C. If we do that, we get the image. Okay, so not too different than the other transformations with the notation. But here we have something a little different. We can see, let's see, we have the pre-image here, okay? And then the image, of course, is a bigger triangle. So we have to believe that this was an enlargement. We see the image is much larger. Now this is a little tricky. The 4 actually does not go to 8 because we're talking about how xt became x prime t prime. And x prime t prime is actually equal to 12. And I think I actually made that mistake the first time I did this. I thought the scale factor was 2, but it's actually 3. So it would be dilate by a factor of 3, centered at the point X, which is a point on the pre-image and the image. Okay. Dilate that pre-image, and that will equal the image. And here's just an exercise for us to kind of find out what happens with the points. What's the coordinate rule of a dilation? And luckily, when we go from the origin, or O, it's quite a bit easier for us. So let's fill in the coordinates real quick. And I'm just pulling these from the graph. Okay. So we see that we're moving from A to A prime, B to B prime, C to C prime. What's happening with the numbers? Well, it's just a straight up multiplication by both coordinates, by the X and the Y. So all you do to dilate from the origin is you multiply the coordinates of the pre-image, the black smaller triangle, by the scale factor. And you might ask, well, how do you figure out what the scale factor is? Well, it's just whatever the points are being multiplied by. And you see we're going from -1 to -3. We're going from -1 to -3, 2 to 6. No matter which of these 6 points, 6 coordinates you want to look at, they all are multiplied by 3, aren't they? So the scale factor must be 3. And we can see that on the picture too. It's a 1/2 here. And then it's like this length is originally where it B's out on the X, and then it triples. And the Y was originally 2, and then it triples and gets up to 6. And then that's where that point goes. So you can even draw a line between every single, it's like a starburst, like it's from the origin. It's like a little explosion, and it's taking all those points. It's multiplying that length from the origin by 3. So dilating by 3 from the origin, do a little O there. Hold on. It's a little bit better. Of any point x, y, it's just the scale factor, which is normally n. In this case, it's 3. So no matter what n is, you just do n times x, n times y. So let's take a quick look here. Let's see. We got -2, 1, and 3, -1. Okay, A, B. And we're dilating by 2 from the origin. So A goes to B. Oh, I'm sorry. A goes to A prime. B goes to B prime. And out of all the rules we've done, I know like switching x and y with the reflecting over the line y equals x was pretty easy, but this one is very, very nice for us. We definitely want to do this by point. So we just have to double all of the numbers. And then if we graph that, let's see, 6, 10. Very interesting looking graph here, right? A prime, B prime. Okay. So the coordinate rule, remember, coordinate rule is saying like, how does x comma y change? And in this case, with the dilation around the origin, you just double the x and double the y. There's nothing more to it. This would be an enlargement, right? Because the scale factor is 2. Let's take a look at one that has a scale factor that's a fraction, a proper fraction between 0 and 1. So we got R, we got T, and we got S. Okay, so if I go ahead and just copy down R, S, and T, if N is 1/2, then I can quickly cut the x and the y coordinate for each point cut it in half. And that would give me my point. So here we get 2, -1. We get -2, 3. And if you 0 divided by 2 is 0, and this would be minus 2.5. A little bit of a decimal there. So where do those go? Well, here would be t prime. Here's r prime. And here is s prime. So that is our image. It's the triangle image. And then here's where it was before. So we see clearly that that black pre-image is being shrunk, reduced to the blue image. And you can also see, again, another strategy would just be to connect the dots to the origin there. And you can see that that's just being, that red distance is just being shortened. Okay, so the rule, just like the other rule, you just take half and half. Okay, whatever the scale factor is, you just multiply that times x or y. Okay, and then a few word problems here. It's natural to be able to talk about how a length changes under different magnification, under a different setting, microscope, anything like that. I mean, you could be making a scale factor if you're trying to make a model train or something, anything like that that has a scale. We could make a problem out of it. So a magnifying glass shows an object, and it shows that it's 7 times. Its magnification factor is 7. That's a scale factor. Okay. Now, the photo shows a 1.75 inch apple seed under the magnifying glass, and it wants us to know what was the original size of the seed if it wasn't under a magnifying glass. We'll call that X. And I already labeled that in our picture. Changes to 7 times. So this formula can help us get set up, which is actually not a new formula. It's just like the image over pre-image equals n. It was the same formula we discussed earlier, final divided by initial. So how can we set up this formula then? Well, the image is equal to n times the pre-image length. Yeah, for these 3 questions, if I just say pre-image, I'm talking about the pre-image's length. So let's see. If we look at it under the magnifying glass, this is the image because it's the image shown by the object. You know, it's a result. Whereas this right here is the pre-image. So if the image's length is 1.75, okay, then to get that, we had to scale the pre-image by 7. So that's why I know it's 7 and not 1/7, because I'm taking the pre-image and I'm multiplying it times that scale factor, making it 7 times longer, and that equals the image. So this is x here. So I can just divide and get 0.25. So that means that this right here is 1/4 inch. Okay, so you take the 1/4 inch thing, you put it under a magnifying glass, it scales it up by 7. That's all that happened. Okay, if you have a document on your computer that is 20.4 centimeters tall, and you do this scale factor thing where it goes from 100% to 25%, it's asking what's the new height. Okay, but that scale factor appears to be 1/4. So if it's true that the image length is n times the pre-image, n is the scale factor, it looks to me that the image was the result of changing that setting. So this should be the image length I care about is h. Scale factor looks like to be 1/4, and the pre-image to start with was 20.4. So the new height should be 5.1 centimeters. Okay. And finally, if we have a microscope shows you that the image, so when I write down my formula, I know for sure that the image, which they don't tell us until here, because they say 40 times, so it must be 40 here to get the 2 millimeters. Okay, so we multiply the pre-image by 40 to get 2, and it's asking what is the actual. Typically actual is going to be our pre-image, so we'll call that x again. So it looks to me that if we divide by 40, we get 0.05 millimeters. Please ask me if you have questions, but this is just an overview. Hopefully this